Hi friends, good morning. In the previous class, we had discussed about the variational method. Variational method we applied to an axially loaded bar and formulated the governing equation, which also gave us the boundary conditions. When the same problem was solved by the mechanics of solids approach, it gave us only governing equation. Right? This is what we had discussed in the previous class. Remember, the classical method gives only the approximate solution. They are analytical in form. Once again I tell you, the classical methods are classified into two types: variational method and weighted residual method. Now we shall see the Rayleigh-Ritz method. Rayleigh-Ritz method is also one of the classical methods. It gives approximate solution. The solution appears in the form of an analytical expression. This Rayleigh-Ritz method depends on the principle of minimum potential energy. In the previous class, we heard about the potential energy, and we also calculated this potential energy for axially loaded member. So here, to calculate the potential energy, we have to calculate the internal potential energy and the external potential energy. The internal potential energy is the strain energy of the solid. The external potential energy is the external potential energy is the work done by external forces. Internal potential energy is the strain energy of the solid. It is due to internal forces. External potential energy is the work done by external forces. Right? And we can also call it work potential. Work potential is always negative because it is the work done by external forces. Okay. Now, we take an example here to determine the potential energy. What example we have? We have a spring here. Look at this figure. We have a spring here. One end is fixed. To the other end, a body of weight W is attached. K is the spring constant, or you can say stiffness. If I give displacement to this weight W, right, and leave it, it vibrates. Okay? Before you attach this weight W, observe the length of the spring. After attaching this weight W, observe the length of the spring. When you attach the body of weight W, the length of the spring increases. So displacement occurs. I say U is the displacement of the spring, or I say deflection of the spring. So what is the displacement of this weight? Same. Therefore, I can also define U is the displacement of the weight. Okay? Right. Now, in this system, I take the spring and I determine the potential energy of this spring. Okay? Now, the potential energy of this spring equals to strain energy plus work potential. Strain energy of this spring, how you determine? Half into Ku square. Half into Ku square. K is the stiffness of the spring and U is the displacement of the spring, or you can say deflection of the spring. Now, the external potential energy, that is simply W into U. So here the external potential energy is negative because it is the work done on the spring by the external force W, therefore it is negative. Now the total potential energy equals to 1 by 2 K U square minus W into U. This is the expression. When the extremum of this potential energy is minimum, then the system reaches the stable equilibrium. In the previous class, I took an example and explained about the stable equilibrium. What was the example? There was a concave surface. A ball, was resting on it. If you give a small displacement to the ball, it comes back to its original position in split second. If you give a small displacement, very small displacement, it comes back to its original position. Its potential energy does not change because it has the state of stable equilibrium. That is what I said in the previous class. Similarly here, this system reaches the state of stable equilibrium when the potential energy of the spring is minimum. Okay. Therefore, we should learn about the principle of minimum potential energy here. What is the principle? It states that of all the kinematically admissible displacements, but we have only one displacement, U. So when you take structures like truss structure, take a two-dimensional truss structure or a three-dimensional truss structure. The truss structure consists of many elements. When the loads act on the truss structure, displacements occur at many points on the truss elements. So therefore, in such a case, we can say, of all the displacements, but here we have only one displacement, that is U. This is the reason why in general, if we state of all the kinematically admissible displacements, those corresponding to the state of equilibrium will extremize the total potential energy. As I said in the previous class, extremum may be maximum or minimum. Those corresponding to the state of equilibrium, observe here, we have only one displacement. So therefore, this U corresponds to the state of equilibrium. I show you another figure. Now you tell me, how many displacements correspond to the state of equilibrium? Right? So this is one spring of stiffness K1. Okay? And this spring is connected to another spring of stiffness K. Okay? Now, say here I apply a force like this. I apply a force like this. Say F. So this is one displacement. Say U1. This is another displacement. Say U2. So how many displacements here correspond to the state of equilibrium? 2. U1 and U2. Right? So therefore, those correspond to the state of equilibrium will extremize the total potential energy. If the total potential energy is minimum, then the state of equilibrium is stable. That is what we see from this principle of minimum potential energy. Right? Now for stable equilibrium of this system, what you have to do? You have to extremize this total potential energy. For extremum of this total potential energy, as I said, d by du of pi equals to 0. d by d pi of u equals to 0. Right? So therefore, if I write here the expression d by du of pi equals to 0. So what I get? This implies 1 by 2 into k. K is the spring constant. 2u minus w equals to 0. This is what I get. So 2 get cancelled with each other. And what you get ultimately? Ku equals to w. Okay? Ku equal to w. What is K? It is the stiffness. U is the displacement. So force displacement relation you get. When you extremize the total potential energy of this system, you get force displacement relation you get. Okay? I said in the previous class, the minimization of the total potential energy leads to formation of governing differential equation along with boundary conditions. So to provide solution to the governing differential equation satisfying the boundary conditions, what we do is, in Rayleigh-Ritz method, we choose an admissible function which contains some arbitrary constants. In Rayleigh-Ritz method, satisfying the governing differential equation and boundary conditions, we choose an admissible function which contains arbitrary constants. Right? So once you choose an admissible function describing the displacement containing the arbitrary constants, you can determine the total potential energy of the system, which you have to extremize with respect to arbitrary constants and each equate to 0. For example, the admissible function contains two arbitrary constants, say a and b. Then you have to differentiate pi with respect to a and equate to 0. Then differentiate pi with respect to b and equate to 0. Which means that you get the number of algebraic equations equal to the number of constants. Then determine both constants and substitute in the admissible function. You get the solution to the given differential equation. This is what Rayleigh-Ritz method says. I tell you, Rayleigh-Ritz method is dependent on the principle of minimum potential energy. To solve a problem by Rayleigh-Ritz method, you have to choose an admissible displacement function satisfying the differential equation, governing differential equation and the boundary conditions, which contains a set of constants. Determine the total potential energy, then differentiate the total potential energy with respect to each constant. You get the number of equations equal to the number of constants. Then solve the equations, you get the values of constants and substitute in the respective equation, you get the admissible displacement function. It is the solution to the given problem. Right? That is what you can see here, taking an example. We have an axial loaded bar, one end is fixed. It carries a concentrated force at the other end. The cross section of the bar is uniform. It is same throughout. Assume that the material is isotropic material. Therefore, which has Young's modulus E, it is constant. L is the length of the bar. Right? Now, I would like to solve this problem using Rayleigh-Ritz method. Okay? So, according to Rayleigh-Ritz method, you have to choose an admissible displacement function. I choose like this, say u equal to a plus px. Why I choose like this? Why not it is a plus bx plus cx square? If you look at the problem statement, so we are instructed to take first order polynomial in x. Therefore, I take a plus bx. If you are instructed to take second order polynomial, then your expression contains plus cx square also. Okay? So, based on my problem, I choose the admissible displacement function u, which is equal to a plus bx. Now, observe this, axial loaded bar, which has a fixed end. Therefore, at x equal to 0, I assume x-axis like this, rightward horizontally, with origin here. At x equal to 0, displacement u equals to 0. This is one condition. Therefore, if you substitute these conditions here, u equals to 0 and x equal to 0, then what you get? 0 equal to a plus b into 0. Okay? Therefore, what you get? A equals to 0. Substitute a equal to 0 here, then you get u equal to bx. Okay? Now, once you get the displacement function u equal to bx, determine the total potential energy. Again, phi equal to the strain energy plus work potential. So now phi equal to, as I said in the previous class, ae by t into integral of, as x varies from 0 to L, epsilon square. What is epsilon du by dx? Therefore, if you differentiate this with respect to x, you get b. Hence, I write in place of epsilon b. So, b square into dx minus work potential. So, what is the force acting at the other end? It is P. Okay? Into displacement. Into displacement. So, what is the displacement? At x equal to L, you get the displacement. This is the expression for displacement. At x equal to L, you get the displacement, at the free end under the action of the force P. Therefore, at x equal to L, what I get? U equal to PL. So, P into BL. Therefore, I get minus P into BL. This is the expression for the total potential energy, which has only one constant. Hence, differentiate pi with respect to B and equate to 0. So, then, what you get? You get an expression like this. And then simplify, you get B equal to P by AE. P is the external force, A is the cross-sectional area of the member, E is the Young's modulus. Now, substitute this B in the displacement function, you get the expression for displacement, which is analytical in form. As I said, classical method gives you a solution which is analytical in form. Okay? Once you get the displacement function, then you can determine the strain induced in the direction of x-axis x. Here we write epsilon xx. If not epsilon xx, you can write epsilon x. Okay? In the coming classes also, we use this type of notation, epsilon xx. What first subscript indicates, what second subscript indicates, that I tell you in the respective classes. Now, it is immaterial whether we write epsilon x or epsilon xx, doesn't matter. Epsilon xx equal to du by dx, which equals to P by AE. And according to Hooke's law, stress by strain equals to Young's modulus. Therefore, stress sigma xx equal to E into epsilon xx, which equals to P by, right? This is the example, which we have taken to understand the Rayleigh-Ritz method. Next, weighted residual method. I said classical methods are divided into two types: variational method and weighted residual method. Now we have come to weighted residual method. In this method, an expression representing approximate solution for displacement is selected. You have to choose an approximate solution satisfying the governing differential equation and boundary conditions. once you are given a problem, you have to choose the solution satisfying the given governing differential equation and boundary conditions, which contains a set of arbitrary constants. Once you choose the admissible function and substitute in the respect to governing differential equation, it results in a residue. The governing differential equation is not fully satisfied because weighted residual method gives you approximate solution, not exact solution. If it satisfies the equation fully, then you get the residue 0. But it gives approximate solution but not exact solution. That is the reason why when you satisfy the governing equation, it results in a residue error. Okay? That residue is made 0 or minimized over the solution domain by multiplying the residue with a weighting function and equating the integral of the product over the solution domain to 0, which is expressed here mathematically. R is the residue. R is the residue. This residue we determine from the governing equation, substituting the assumed function. This residue is multiplied by a weighting function and the product is made 0 over the domain where, this is omega, this is gamma, over the domain, or you can use omega also. Integral of WR the gamma equals to 0. Okay? W is the weight or say weighting function. And again, these weighted residual methods are classified into 4 types. The first one is collocation method, second one is subdomain method, third one is method of least squares, and fourth one is Galerkin method. You can use any one of these schemes under weighted residual approach. The first one is collocation method. In this method, we choose the discrete points that represent collocation points. We say points of collocation. We choose the discrete points as the points of collocation. At each of these collocation points, the residue is made 0, is forced to 0. This we can understand well taking an example in the next class. Right? As a result, the differential equation is satisfied at each of the collocation points. Okay? If you choose a governing equation like this, say let L of phi equal to 0. This is the governing differential equation. Okay? Now, given differential governing equation with boundary conditions. The boundary conditions are not specified here, subject to the boundary conditions. So we give the differential equation. Now, we choose the approximate solution satisfying this differential equation. Then, how you get phi equal to the sum of as I varies from 1 to n, ai into ni, where ai are the arbitrary constants and ni are the known functions. Remember here, how many collocation points you take, the number of collocation points depend on the number of unknowns. So when your selected function contains 2 arbitrary constants, you have to choose 2 collocation points. When you choose an admissible function with 3 arbitrary constants, you have to choose 3 collocation points. Then only you get the solution. Okay. Now let us see the summary. So what we have learned in this particular class, we have discussed about the Rayleigh-Ritz method. Rayleigh-Ritz method is one of the classical methods. It is dependent on the principle of minimum potential energy. We had learned determining the potential energy. We also learned determining the minimum potential energy according to the principle of minimum potential energy. What the principle of minimum potential energy states? Of all the kinematically admissible displacements, those corresponding to the equilibrium will extremize the total potential energy. If the extremum is minimum, then it reaches the state of equilibrium. This is what the principle of minimum potential energy states. Right? So what the Rayleigh-Ritz method says, it says you have to choose an admissible function satisfying the governing differential equation and boundary conditions. Then we have to determine the total potential energy. Remember, the admissible function what we choose contains a set of arbitrary constants. So therefore, after determining the total potential energy, we have to differentiate the total potential energy with respect to each constant. Then we get a set of equations, algebraic equations equal to the number of constants. Then we solve them for getting the values of arbitrary constants. We substitute in the respective equations. Then we get the solution for the given problem. And later what we have learned, the weighted residual method. There are 4 types of weighted residual methods. Method of point collocation, subdomain method, method of least squares, and Galerkin's method. Method of point collocation we have discussed. In the next class, the remaining 3 methods we discuss and do some problems. So thank you very much.